This is 3t and 3u. We're looking at the derivatives of logarithmic and exponential functions. We already know how to take the derivative of the trigonometric functions. We know how to take the derivative of polynomials. We know how to take the derivative of radical functions, except for the square root, because you put it all to the 1/2 and apply the chain rule. Rational functions, something over something else, use the quotient rule. But we do not know how to deal with logarithmic and exponential functions, okay? So the first thing that we need to do is actually recall what is a logarithmic and an exponential function. So let's review that here. So an exponential function would be something like this: y equals b to the x. So for example, y equals 2 to the x. You might be like, I already know how to do that. And I would say, or I mean, I already know, we've already talked about this kind of stuff. And I would say, no, you haven't. What type of functions have you seen before?
X to the x to the something.
X to the something, x to a number, right? Where x is the base and the constant is in the exponent. Now we are dealing with a completely separate type of a function. This is where the constant is the base and the x is the exponent. And the graphs of those two are extremely different. This one goes up pretty quickly, but this one just blows it away. If you would think about just like the shape of it, how quickly it rises. Okay? Y equals 2 to the x, 5 to the x, 10 to the x. Those are all pretty common. There is a very special function where you have y equals e to the x, where e is known as Euler's number, because it was named after a guy whose name was Euler, E-U-L-E-R. We'll read about him in a few weeks. But anyway, e is a constant, just like pi. It's approximately 2.718, and it continues. It's irrational, and it's pretty cool, I'm not going to lie. E is one of the most amazing numbers ever. I'd say it's even more prevalent than pi. It's up there with pi, I, -1, 0.
Golden ratio.
Yeah, oh, golden ratio. Yeah, absolutely. All right, these are what we would call exponential functions. And if you remember from pre-cal, or even if you don't, here you go. There is a way that you can convert these to a logarithmic expression of it, logarithmic equation. And what you do is you write the word log, L-O-G, and then in the subscript position, you put the base of what was over there on the other side, and then in, I would call the parameter position, I'm sure there's a more technical term, I don't know what that is. You put the exponent, whoops, sorry, you don't put the exponent. You put the power, and then over here you put the exponent. The temptation is to put the b right there and then the x right there, so it looks like b to the x, just like you've got b to the x, but that's not what it is. It's log base b of y equals x. And what that means is, if you have base b and you raise it to the x power, then you get y. Alright? So for instance, if you have log base 10, and the answer of this power thing is 100, then the number over here is 2. Log of some number means show me the exponent. Means I'm doing right now all this stuff over here. Show me the exponent that leads to, you know, something like this. 10 squared equals 100. So numbers, but they're just in different spaces, right? It's 10, 100, and the number 10, the number 100, the number 2, but here, this one's down here, and this one's over here, and that one's here, but over here, it's this one's here, this one's here, this one's here. It's just, logarithms allow you to kind of go the opposite way. If you're like, I know what the answer is, so to speak, and I know what the base is, but I want to figure out what the exponent is. Anyway, there you go. So that's logarithms. Okay? And there's graphs and lots of stuff like that. And you can convert back and forth. So let's apply that knowledge. Anybody want to venture a guess? How could I rewrite this exponential equation as a logarithmic equation? Yeah, there you go. Log base e of y equals x. Now that number e is so common that the log base e we sometimes write as ln, which is short for the natural log. You might say, wouldn't that be short for log natural or something like that? Like, oh well, don't ask me. So, if you see ln y, you think that's log base e of y. Might as well tell you this just as a little side note. Sometimes you'll see something written like log of 50, but there's actually no subscript there, okay? On calculators and textbooks, this is usually understood that there is an implied 10 right there. With your calculator, if you just hit the log button, I don't think, and you do log and then you type in 100, what does it give you? 2, right? But you're like, where's go grab a calculator, come on, don't be shy, be responsible. Alright? Where's the 10? Where's the 10? It's implied. Okay? Now, I'll just tell you this because some of you are going to go on to do bigger and better things in mathematics, and you'll probably use a software tool like the Wolfram Alpha website or Mathematica or something like that. And on those tools, you go to Wolfram Alpha and you type in log 50 on Wolfram Alpha, which is a website. Then there is an implied e. What's that? So, like for instance, if you type in log 50 on the Wolfram Alpha website, it's going to assume what you mean is log base e of 50, not log base 10 of 50. I think they've kind of cleared that up a little bit. Where now, I think I remember seeing something in the last year that if you typed in log, then anytime they had some sort of like if statement in their code that said, if the user's doing something with log, add this little bit of a blurb to let them know, hey, when we write log, we mean natural log. When we write log base 10, we mean log base 10. But there you go. There's some stuff there. So I'm gonna write f of x equals e to the x. That's the definitive exponential function. And it is true, if I'm going from here to here, y equals that the inverse property of e to the x is natural log. If you remember, every math operation has his evil twin, his arch nemesis. Addition has subtraction, multiplication has division, sine has inverse sine, functions have inverse functions, okay? So if square has
it's radical.
Yeah, the radical square root. E to the x, his equal and opposite is natural log of x. Okay, so they reverse operations. And just as a reminder, the graphs. So e to the x is going to something like this. It's asymptotic here along the x-axis. And natural log is, I don't know if in algebra 2 you talked about this, but the relationship between functions and their inverses, when it comes to the graphs, it's actually reflected across the line y equals x. I don't expect you to have that memorized, but. All right, so this is all still kind of like the pre-calculus part of things. This is just talking about these functions. Yes, Chloe?
Well, where did you get f to the negative 1x? Like,
that's called the inverse function. That's when
okay.
Instead of going from the domain to the range, you map from the range back to the domain. It's not derivative.
I know,
Okay.
that's why I was kind of like.
Yeah, no, it's not. That's another kind of yeah. You go like the first derivative and the second derivative comes like a 1 and a 2. Like this would be like the negative 1 derivative. It would be like the antiderivative. Oh wait, that's the next chapter.
Oh, there actually is.
No.
Yeah, there's an antiderivative. I told you that every mathematical operation has its invert, or has its,
like
you know,
the evil
twin, right? Yeah, there is a reverse process for derivatives.
Whoa.
And guess what? It's analogous to the relationship between multiplication and division.
No.
AKA, everybody loves multiplication, but everybody hates division, right? Am I right?
Yeah.
So guess how you're gonna feel about antiderivatives? You're gonna love them. Anyway, all right. Spoiler alert. Okay, let's go ahead and apply what we did a few weeks ago. That is we'll start to get a little bit calculus on this. Now let's go do some local linearization. Let's pick a few points along this graph, and let's draw some tangent lines. Okay, so if I were just to kind of have another point pretty close to that, you know, what would that secant line look like? Remember that sort of game that we played there? And then we'll do the same thing over here. I'm not going to tell you what the derivative is quite yet. We're going to derive it. But looking at the slopes here, what sort of numbers are we seeing here? Positive numbers, negative numbers? Positives. Okay, I'm going to say this looks pretty steep. Like that might be like a 10, right? If that's a 10, what might this number right here be? 8. Maybe an 8. 6. I'll put a 4, a 2, and a 1. This number's getting kind of close to 0. In fact, it actually does kind of flatten out and becomes really, really close to 0. I'm going to put a 0.1 right there. And we'll go ahead and run the cycle on this one. So remember, if we're talking about the derivative, so this is f prime of x, the derivative has the slopes here are the y values on the derivative. So this would be a y value, an up-down value of 0.1 at that same exact spot. So probably actually a little bit lower than. Let's make it a little bit lower. And then 1, which is a little bit higher than that, and then 2, which is a little bit higher than that, and then 4, which is a little higher than 8 and 10. And kind of interesting, the shape of the derivative graph. What do y'all notice about the shape of the derivative?
It's kind of the same.
Kind of the same, okay? We'll see some real interesting things about that. And some of the neat things about the weird. Let's throw some numbers here at the logarithmic graph. What sort of numbers are we looking at? Positive, negative?
So
For the slopes? Well, you
that
might
one's
think
pretty- that
it's
one's
in negative territory, but the slope is actually positive. Remember, if you're standing here looking this way, you'd be like, I want a really steep slope, right? Okay, so it's like a 10. This might be like an 8, then a 4, then a 2, then a 1. And we're actually getting closer to like a flat. I'm standing on flat land rather. I should do that one right there, you know? So then down here, I'll write the derivative f prime of that. Actually, it's f prime inverse, but anyway. And once again, if you remember, the slope values here correspond to the y values, the up-down values here. So right around the y-axis, I've got slope of 10. That's going to correspond to like a y value of 10. So it's going to be up here. This would be a y value of 8, a y value of 4, and 2, and 1. And 0.1, it actually kind of looks something like that. So if you're thinking that that the derivative over here of the logarithm graph would look like the graph of the logarithm, then sorry to disappoint you. So. Okay. That's what logarithms are. This is what the graphs look like, plus a little bit of calculus. Now we're going to kind of go back, though, and there are some properties of logarithms that we're going to talk about. Some of them you will remember happily. Some of them you probably never knew or thought about. But here we go. Trying to think if there's... We'll carry on here. So here you go. Still trips down memory lane. These are properties, I guess you could say. The natural log of e is equal to 1. You can try that out with a calculator. Do you know how to get the e button? Here's a hint. It's not alpha e. It's not going to be second and then sign. It's going to be second and then ln. And it's naturally going to give you an exponent for that, so you just want to leave that at 1. Leave that at 1. But there you go. ln of e to the 1. Because let's play the game. The natural log of e equals, I don't know. Let's convert this logarithmic equation into an exponential equation. So kind of go back and play that game here. Can y'all do that?
Yeah.
What's the hidden base here that we never actually see? E. Okay? So that's the base, so I'm going to write that as the base. Where is the exponent in this equation? Is it the e or the question mark? It's the question mark. So e to the question mark equals, and then this e right here is whatever that answer was. So e to the question mark equals e. Well, this e has an implied 1 right there. Ergo, question mark must equal 1. And since question mark was equal to the natural log of e, then natural log of e is equal to 1 by the transitive product. Okay. B to the 0. Any number to the 0 power, I think you probably have that fact memorized, is what?
It's 1.
Is 1. Now let's convert that to a logarithmic equation. So log base. No. Still wrong. The base, okay, corresponds to the base.
Oh yeah.
That's the base position. This is the exponent position. this is what we call, this is the power. Okay? So log base b,
Of 1.
that's the base
And then it's
of 1, that's the power, equals 0. That's the exponent. This is a happy little diagram which I'll let you copy down with the labels.
Wow.
Applying that knowledge, the log base 10 of 1 is
Log base 10 of 1 is going to be log, no,
It's gonna be 10 equals, oh,
Zero.
0. The log base 7 of 1 is
0.
0.
I'm trying to do smart.
The log base y of 1 equals 0. In fact, the log base b of 1 is 0. Anytime you have the log and then
One.
your power right there is 1, then your answer is going to be 0. Okay? Properties, properties, more properties. The whole rest of this class is going to be properties. Just give me a heads up here. E to the ln of x equals, well, let me tell you this.
Log e.
If I'm standing in some position and I go -2 and then +2,
Back in the same spot.
back in the same spot, right? So I have x, I take the natural log of it, and I take e to that answer. E to the ln of x is x. Why? Because, well, I'll show you. Here, because BC. If I were to say, I don't know what it is, it's question mark. Can you convert this exponential equation into a logarithmic equation? Sure. I'll say log base e of power question mark equals exponent, natural log of x. Well, what's log base e? What's the short version of that?
Natural log.
Natural log. So natural log of question mark equals natural log of x.
Oh.
Right?
Yeah.
Ergo question mark equals x. Ergo e to the ln x equals x. More properties. Natural log of e to the x equals 1. Because that's what p/c is. Let's play the game. Can you convert that logarithmic equation into an exponential equation? Base.
Log.
Oh.
No. Oh, no.
I've got a base right here, a hidden base e.
Yeah.
Hold on. That's not the game we'll play. We'll play this game. Natural log e to the x equals question mark. So that would mean hidden e right here. This e to the question mark equals all of this stuff that's inside of the power, right? E to the question mark equals whatever's inside. So question mark equals x. Here's some that I will show you without verification because we've done these so many times. The log of A times B. Remember this? The log of A plus
The log of B.
the log of B. The log of A divided by B, you can probably guess.
Log of A minus log of B.
The proof is not difficult and it's kind of fun, but that's pre-cal kind of fun. We have calculus fun in here. The short way that I can kind of remind you what the basis is this is based on what goes on with exponents when you multiply the bases and stuff like that. If you remember, like, if you have x squared times x to the third, what do you do with those exponents?
You add them.
Add them. It's x to the fifth. So the multiplication of the bases turns into the addition of the exponents. And so here you have the multiplication of the bases and the addition of the exponents. So it's logarithms. Same thing with division. If you have x to the seventh over x to the fourth, what did you do in that situation?
Cancel out.
You canceled them out. Shorthand also, you could do the 7 minus the 4. I don't know if you ever did that. Okay. So the division of the bases turned into subtraction of the exponents. So here you have the division of the bases. Oh, let me. Nothing there. Turns into subtraction of the exponents. All right. Third property. Log of A to the B equals B times log A. And this is true for any base. Base 10, log base 10, log base E. So it works for natural log base 2. You do a lot of log base 2 in computer science. All right, last property here. Any number b to the x can be written as e to the ln of b to the x, which in turn can be written as e to the x times ln b. You're like, wait a second, what gave you the right to bring that x down in front? The thing I just wrote up here. The log of anything, and you've got the power inside there. Notice you just pop it down. It's kind of almost like a precursor to the power rule. See what I'm saying? But you don't like decrease the exponent. You just kind of put it out front there. So I kind of put that x out front there. Now, if you want to know the reasoning a little bit behind that, e to the ln of b to the x equals question mark. All right. If I take the logarithm, the log base e. Let's see, hold on. How did I do this silly thing here? Next line I have log base e of question mark equals ln dx. Oh, I just converted this exponential into a logarithm. So this is base exponent power base, right there, exponent, or sorry, power over here, exponent. And then log base e is ln. So question mark equals b to the x. All I'd say though, we're going to be utilizing that fact right there. Hooray! That's everything pre-calculus that you need to know for the next week as we dive into the calculus. Just enough time. Here we go. If you ask me, this is the real interesting stuff. All right. Here is what we're going to find. Find the derivative of e to the x. Okay? Now, we already have a kind of an idea about what the derivative of e to the x is going to look like, because we saw that it was, the shape is going to look something kind of like this. Okay? So let's go ahead and play the game. So here we go. F of x equals e to the x. Now, if you remember, how do we find the derivative? Nope. Drop down, power down, drop down, power down, pop down, power down. Only works when you have an x right here and a number up here. Doesn't work when you have a number here and an x up there.
That was the log and then base and power.
No, can't. None of those things are right. We've got to go with the definition of the derivative.
Yeah, the derivative, the change in, no, the slope of the tangent line.
Slope of tangent line, which you get by applying the limit process to the slope of the secant line, f of x plus delta x minus f of x all over delta x. So that's going to be the limit as delta x approaches 0. Let's go ahead and apply it here. So I'm going to plug in x plus delta x every time I see an x up here. So this is going to be e to the x plus delta x minus e to the x all over delta x. Chloe, you're making an expression on your face which makes me think you have a question.
No, I'm good.
See how just applying it? It's just applying the difference quotient there. Okay. So, where are we going to go from here? Well, just a bunch of algebra. If you remember from algebra, anytime that you have a situation where you have a base and you're sort of like adding those two things, we could actually do the reverse process and split this up into an e to the x times e to the delta x. Now, you probably never did that in your life before, because normally what you would do is when you had, normally you would go the reverse way. Normally you would have like e to the blah and e to the blah, and they're multiplied, and so then you would do the e to the blah plus blah. But we're just pulling it out there. And the reason why we're pulling it out, because now we can see that both this term and this term have an e to the x. And that means we can factor out an e to the x. All right? Yeah, you were close. Kind of. I appreciate the enthusiasm. So we've got e to the x times, I'll put a bracket, e to the delta x minus 1 over delta x. So you see I'm just factoring out an e to the x. Okay. Now answer me this. As my delta x changes, as it gets closer and closer to 0, so it goes like from 1 to 0.1 to 0.01 to 0.01, That's changing. Is it changing e to the x at all? I'm just changing the delta x, right? So actually this thing I can pull outside and as a multiplier here. So it's e to the x times the limit as delta x approaches 0 of e to the delta x minus 1 all over delta x. Great. Let us review how we calculate limits. Oh my gosh, everything just goes back to limits. What are our tools for solving a limit problem?
You can plug in the 0
Plug it in.
and wherever the
And 0 there and 0 there.
oh, but you can't
Direct substitution fails because
of the
There's
0
a
in the
zero on the
denominator.
denominator. So what are some of our other tools?
We
They're
can't.
long.
Calculator,
What part of the calculator?
graphing part where you auto.
Okay, yeah, we could graph it and then kind of try to trace along. Okay. Another method was,
There was factor. No.
yeah, you could factor it, multiply by the conjugate, all that stuff like
Oh
that.
yeah, that.
Let's just go with the table, folks. Can you just do with the table?
Oh, the table. I forgot.
Let's just go with the table, okay? So what you're gonna do is on your f of x, you're gonna just type in e to the x minus 1 over x. Right? That's the function that we're gonna type into the calculator. Actually, it could be like y equals. Alright, so there's 0, so here's our x, and then here's our y values. Ladies, go ahead and type in, go to the table and type in -1, -0.1, and -0.01. Guys, you type in 1, 0.01, 0.1, and 0.01. And use that table feature, and I'm gonna need y'all to call out those numbers to me. So ladies, y'all are working the negative side. You guys are working the positive side. And just as a reminder, what we're doing is we're solving that part. Alright guys, gentlemen, do you have a number for 1? What is the... Sure, Hector, just say it. I'll give verification or we'll shut you down.
1.72.
I hear 1.72. What about for 0.1?
1 is negative 8.9.
Yeah, that's alright. Ladies, do we have a value for -1?
Yeah, it's 0.63.
What about -0.1?
0.95.
What about -0.01?
0.995.
0.995. Ooh. Just out of curiosity, what's -0.001?
0.9995. 3 nines.
3 nines. 0.9995. Okay. Guys, how about what are we getting over here for 1? 1.72. What about 0.1?
1.05.
1.05 and 0.01?
1.005.
1.005. So class, what does it seem like we this expression is approaching?
1.
I agree, it's approaching 1. From the left and from the right, we're approaching 1. So, I'm going to say this, so e to the x times 1. That's pretty handy. So wait a second. On the right hand side I have e to the x. What's on the left hand side? F prime. Wait a second. Are you telling me when I've got f of x equals e to the x that the derivative is equal to e to the x?
That's great.
Yep, it is. The derivative is exactly the same as the original function.
Wow.
What about the second derivative?
So
Just take the derivative of this.
yeah,
What's the derivative of e to the x?
it's gonna be
E to the x. Right?
Mhm.
Because the derivative of e to the x, if you got e to the x, take the derivative of that, it's going to be e to the x. What about the third derivative?
Still gonna be.
It's still e to the x, yeah. It's like caught in a loop here, right? Okay. Remind me tomorrow, that's what we'll talk about. We'll do the chain rule on this and have a new formula to add to our memorization. So yes, reminder, memorization quiz on Friday. It's basically going to be the redo from last
Oh.
plus the pieces. There is no homework due tomorrow other than the second half of the notes on 3-9. Hooray, you're welcome.
Thank you.